My dear students, let me welcome you to the General Revision Edition. Write the scientific term. The magnetic flux which induces an EMF of 1 volt in a single turn, one-turn coil, when the flux is reduced to 0 in 1 second. Yes, thank you very much. It is the Weber. So it is the Weber. Another scientific term, magnetic flux density of a uniform magnetic field which produces a force of 1 Newton on a wire 1 meter in length carrying a current of 1 ampere when the wire is placed perpendicular to the field. Yes, magnetic flux which produces a force of 1 Newton. It is the Tesla. Thank you. The instantaneous EMF induced in the coil of an AC dynamo. When the plane of its coil makes an angle 45 with the field. At this particular instant, the instantaneous EMF will be equal to something very important, which is, yes, the effective value. The effective value of the induced EMF. An EMF of 2 millivolt is induced in a coil when the current flowing through this coil changes at a rate of 1 ampere per second. What does this mean? Yes, self-inductance of a coil, self-inductance of the coil is 2 millihenry. The ratio of the electric power or electric energy produced in the secondary coil to the electric power consumed in the primary coil of a transformer, yes, equals 0.9, is 0.9. What does this mean? Okay, efficiency of the transformer is 90%. Efficiency of the transformer is 90%. Also, we can add something here. Yes, we can say the ratio between the produced energy or power, VSIS, over the input power, VPIP, is equal to 90%. The direct current, once again, let me remind you with the title of the question, write the scientific term. The direct current that produces the same heating effect per second as that produced by an alternating current is 10 amperes. It's all easy for you. It is the effective value of the AC current. So effective value is equal to 10 amperes. Another type of questions. What happens when the 2 metallic rings in an AC dynamo are replaced with a split cylinder commutator? Okay, the AC current becomes unidirectional but varying current. It is shown in front of you right now. So once again, the AC current becomes unidirectional but is still changing. What happens when the shunt in an ammeter is replaced with another of lower resistance? Okay, with respect to, it asks with respect to the sensitivity of the meter and the maximum current that the meter can measure. What happens to the sensitivity when the shunt is replaced with another of lower resistance? Okay, sensitivity decreases, and this means the meter can read greater currents. What happens or what will happen to the reading on the hot wire ammeter? Hot wire ammeter is a device for measuring AC currents and DC currents, of course. What will happen to the reading on the hot wire emitter in the circuit when the key is closed? Yes, when the key is closed, this means we are connecting another capacitor. So when connecting capacitors in parallel, capacity increases and XC equals 1 over 2 pi FC. So when capacity increases, reactance decreases and the current increases. So once again, since the capacity of the capacitors increases when connected in parallel, so the capacitive reactance decreases. Capacitive reactance equals 1 over 2 pi FC. C increased, XC decreases. Reactance is like any opposition. When it decreases, the current increases. What will happen to the reading on the voltmeter in the shown circuit when the value of S is increased? The question now, what does this voltmeter read? Actually, it reads the potential difference across R, which depends on the current. When we increase the value of S, the current decreases, so the voltage decreases. The reading on the voltmeter decreases. Calculation of the EMF induced in a straight wire moving in a uniform magnetic field. We'll try to calculate to determine the size of the EMF induced in a straight wire moving in a uniform magnetic field. PQ is a straight wire of length L. The wire is free to move, yes, in a uniform magnetic field, yes, of flux density B. Suppose that the wire is pulled with a uniform velocity V to move a distance delta x in a time delta t perpendicularly to the field. Okay, so once again we've got a wire PQ. The wire is pulled to move a distance delta x in a uniform magnetic field. Direction of motion is perpendicular to the field. The field is denoted by X. It means the field is directed down into the page or into the screen. From Faraday's law, EMF is equal to N delta phi over delta T. We don't have any terms, so EMF is equal to delta phi over delta T. So EMF is equal to delta phi, yes, is equal to magnetic flux density times the change in the area of the linked flux lines over delta T. So delta phi, which is equal to B delta A over delta T. As I said, delta A equals delta X times L. So EMF equals delta X times LB over delta T. Delta X is distance. Distance over time gives the velocity. So we can say EMF is equal to negative sign BLV. Okay, where in this particular case, the wire moves perpendicular to the field. Your attention, B is the magnetic flux density, L is the length of the wire, V is the velocity with which the wire is moved. In general, EMF is equal to negative BLV sine theta, where theta is the angle between the direction of motion of the wire and the magnetic field. And now, talking about the EMF induced in a wire moving in a magnetic field, the factors affecting the size of this EMF. First of all, magnetic flux density of the field. So density of the field is the first factor affecting the, EMF induced in a wire. Length of the wire, okay, and velocity of the wire. And finally, find the angle between the direction of motion of the wire and the magnetic field. All factors, are taken from the expression EMF induced is equal to BLV sine theta. And now let's try to solve some problems. First problem, a coil of area 8 centimeter squared. So area of the coil is 8 centimeter squared. And 300 turns, number of turns on the coil is 300, is placed at right angles to a magnetic field of density 5 times 10 power negative 3 Tesla. We want you to calculate the average EMF induced in the coil, okay? In the following cases, when the coil is rotated through an angle 90 in 1 second, okay, when the coil is reversed in 0.1 second, when the magnetic flux density through the coil is increased to be 9 times 10 power negative 3, and instead of being 5 times 10 power negative 3, we'll increase it to be 9 in a time of 0.1 second. And finally, when the coil is removed from the field in a time of 0.1 second. We'll take it one by one. The first case, when the coil is rotated through an angle 90. Okay, EMF is given from Faraday's law. EMF is equal to N delta phi magnetic over delta T. Coil is rotated through an angle 90. Delta phi equals phi. So EMF equals negative sine N phi, which is equal to A, and change of the magnetic flux density over delta T. So we can say EMF induced is equal to negative 300. 300 is the number of turns. Okay. Area of the coil is 8 centimeters squared. To convert from centimeter squared into meter squared, so it is multiplied by 10 power negative 4. Okay, a change in flux is from 5 times 10 to the power of negative 3 to 0. So 0 minus 5 times 10 to the power of negative 3 over 1. This happened in a time of 1 second. Okay, so EMF is equal to 1.2 times 10 power negative 3 volt. In the second case, when the EMF, when the coil is reversed, what about the EMF when the coil is reversed? Okay, when the coil is reversed, the change in the magnetic flux, delta phi magnetic, is equal to, phi magnetic. So it is equal to 2 times A times B. We'll use the same rule. Okay, Faraday's law, EMF induced in this case will be equal to negative sign, which indicates Lenz's rule. Number of turns 300. Okay, between two brackets, 2 times 8 times 10 to the power of negative 4 times 5 times 10 to the power of negative 3, and time is given to be equal to 0.1. So EMF is equal to negative 0.024 volt. So your attention, when the coil is reversed, delta phi magnetic equals 2 phi, and phi is equal to the product of area and flux density. Okay, and what about when the magnetic flux density through the coil is increased from 5 to 9 times 10 to the power of negative 3. Once again, same formula. So MF equals N delta phi magnetic over delta T, delta phi magnetic A delta, yes, beta over delta T. So number of turns 300 times 8 times 10 to the power of negative 4. 8 times 10 power negative 4 is the area. B is changed from 5 to 9. So the difference 9 times 10 power negative 3 minus 5 times 10 power negative 3 over the time. This happened in a time of 1 second. Okay, this happened in a time of 0.1 second. The EMF will be equal to, yes, minus negative sign 9.6 times 10 to the power of negative 3 volt. And finally, when the coil is moved away from the field using the same rule, okay, now the coil is subject to the field and is removed from it. Okay, so we've got a change of phi. So number of turns 300, area 8 times 10 power negative 4. Final flux is equal to 0, initial 5 times 10 power negative 3 over 0.1. It is equal to 0.012 volt. Another problem, a circular loop in the plane of the paper, plane of the screen, lies in a 3 Tesla magnetic field that points down into the page. The loop's diameter, it changes from 100 centimeter to 60. So the area is decreased, diameter is decreased. So we are decreasing the magnetic flux passing through the loop. So the induced current will be in the same direction. Once again, circular loop in the plane of the paper lies in a 3 Tesla magnetic field that points down into the page. The loop's diameter changes from 100 to 60 centimeter in a time of 0.5 seconds. What is the magnitude of the average EMF? What is the direction of the induced current? Magnitude is determined from the expression EMF equals negative N delta phi magnetic over delta T. So it is equal to negative N magnetic flux density. The change in this problem is in the area, in the diameter. So it is equal to negative NB delta A over delta T. It is equal to minus 1, 3 pi between two brackets, 0.3, yes, squared minus 0.5 squared over 0.5. Okay, the EMF is equal to 3.017, and its direction, as I said, it is clockwise. Another problem, if a coil of 150 turns is linked with a flux of 0.01 Web. So turns number is 150, phi 0.01 Web. When carrying a current of 10 amperes, calculate the inductance of the coil. We want coefficient of self-induction. And if the current is reversed in a time of 0.01 second, calculate the induced EMF. So talking about the inductance, EMF induced is equal to negative N delta phi magnetic over delta T, and also it is equal to negative L delta I over delta T. So we can say L is equal to N delta phi magnetic over delta T. Number of turns is 150. Change in flux is 0.01 and the current is 10, so it is 0.15. H stands for Henry. So inductance equals 0.15 Henry. Okay, and what about when the current is reversed? When the current is reversed, the current is multiplied by 2. Current was given to be equal 10. So in the expression, it will be 20. L is equal to inductance 0.15. Current, as I said, 10 times 2, so it is 20 over the mentioned time. It is 0.01. So the EMF induced is 300 volt. Since EMF induced is, yes, determined from N delta phi magnetic over delta T, so this is another method to calculate the EMF induced using Faraday's law. Current is reversed, delta phi, yes, equals 2 phi. So once again, 150 times 2 times 0.01 over 0.01, the same answer, it is 300 volt. And now we've got a question in front of you. We've got, yes, a circuit. What about the circuit? We've got a cell, VB. Okay, EMF of the cell is VB, internal resistance is small r. And we've got two resistances. R1, it is variable resistance. R2, which is a fixed resistor. Okay, and we've got two voltmeters, V1 and V2. V1, as a matter of fact, reads terminal voltage, but V2 reads the voltage just across R2. V1 reads the voltage across R1 plus R2. Okay, it reads the terminal voltage. And what about the question? Yes, the question says, what would happen to the readings on the 2 voltmeters if R1 was increased? So increasing R1, will it change the readings on the 2 voltmeters? What is your answer? Okay, we'll take it one by one. First of all, we'll say the answer, we'll mention it, then we'll explain it. V1, the terminal voltage, increases when increasing the resistance. But V2, the voltage across the fixed resistor, decreases. V1 increases, V2 decreases. And now, high time to explain it. Explanation, what about the, yes, question? Since the current through the battery, mean current, is determined from V sub B over R equivalent of the whole circuit. V battery is constant. It is not changed. We didn't alter the battery. So the current is inversely proportional to the total resistance. And when R1 is increased, okay, it is inversely proportional since V battery is constant. Okay, and V internal is equal to IR. And there's something we should mention here. Increasing the value of R1 will increase the total resistance of the whole circuit. Thus, the current through the battery will be decreased. But V internal is determined from the formula I R small. R small is constant. Okay, it's not, yes, it hasn't changed. So internal volts depends on the current. What happened to the current when we increased R1? Okay, increasing R1 will increase the total resistance, will decrease the current. So internal voltage will be decreased. Okay, once again, since R, small r is constant, internal voltage is proportional to the current. Okay. And there is something very important. V internal is decreased as it depends on the current. But V internal plus V external is equal to V battery. And the battery, okay, we didn't change the battery, so V battery is constant. Okay, so we've got an inverse relation between V external and V internal. That's to say, when V internal decreases, V external, yes, increases. Okay, so once again, V external plus V internal is equal to a constant, which is V battery, V sub B. Okay, internal is decreased, so external voltage is increased. So once again, when the resistance R1 is increased, total resistance increases, current through the battery, yes, decreases, internal voltage decreases, but V external will increase, V1 will increase. Still something we want your answer. We want you to answer it. V2, what about V2? It is the voltage across R2. What about it? Okay, before we're answering this, let's sum it up. When R1 is increased, when R1 increases, current decreases, and so does the internal voltage, therefore external voltage increases. And what about V2? V2 is equal to IR2. So it depends on the current, the same, yes, at the internal voltage. Why? Because R2 is constant. R2 is constant, so it depends on the current. What happened to the current? It decreases, so V2 decreases. Okay, so V2 is proportional to the current as R2 is constant. When the current decreases, V2 also decreases. So we managed to explain it. Okay, another type of question, what would happen to the readings on the voltmeters if R1 was increased? The circuit will be shown in front of you right now. Okay, what would happen to the readings on the voltmeter when R1 was increased? So we'll increase R1, okay, and we want you to answer. Will the reading of the voltmeter increase, decrease, or unchanged? Your attention here. The first, yes, question you have to ask yourself is, what does this voltmeter read? Actually, it reads the potential difference across R2, which depends on the current. So the voltmeter in front of you reads the voltage across R2. R2 is constant, so it changes when the current changes. If the current is increased, it will increase, and vice versa. Okay? Okay, in the problem, we increased R1. Okay? We increased R1. Okay, the voltmeter reads the voltage on R2. The reading on the voltmeter equals IR2. Okay, when the value of R1 is increased, the current decreases. So the reading on the voltmeter decreases as R2 is unchanged. So it depends on the current, and the current was decreased when R1 is increased. In this way, we've come to the end of the General Revision Edition. Until we meet again, my best wishes to you all. Thank you.